Maybe I'm gonna talk about some other things before we start the basic of the programming. Yep. So for today, we're gonna do some hands-on programming. So if you brought your laptop, then maybe at the second time, you're gonna fork a repository and we're gonna do some hands-on programming together. But maybe in May, I'm gonna visit here twice again to give you more interesting topic that I am researching at the Ethereum Foundation, which is mostly about the applied cryptography and zero knowledge proof. I'm pretty sure that if you like some mathematics and computer science, then you might be definitely interested in those topics. Yeah, let me introduce myself first. I am now working as a ZK researcher at the privacy and scaling team at EF, and also work as a steward of the general echo dev team at the EF, which is helping people like you. So it's discovering potential talent in the community and giving you some support that we can give you. And also, I am your 선배. So I am mechanical engineering 기계 공구학번, and I just graduated school like about at 2014. So by the way, today we're gonna talk about the hands-on programming, but there is something that you have to keep in mind when you do something on Ethereum. So I'm gonna talk about that first. Ethereum is not just only a technology. What do you think with this slide? This is an event which is being held in Montenegro from March. And this is a pop-up city for the network state citizens, which means people are trying to build a virtual city, virtual state among the people who are sharing the same value with each other. This is called Zuzalu, and people are getting together there and trying to build some experimental tries there. The reason why I'm talking about this is about for the Ethereum, the people are the most important thing, because we are just a community and we are building our world using the technology. So I think it would be helpful for you to share my experience from about 2012. Actually, Professor Han briefly introduced, so thank you so much for about that. And just to share my previous experience, around 2012, when I was the senior in KAIST, I started to make a startup with my friends. And that startup was about developing some workout pattern analysis algorithm based on machine learning. So it is acquired by another AI startup in 2014, because 2013 was a kind of a very big year for the deep learning. So at that time, I just swapped my all equities to the new company, which acquired my company at the time. And during the period when I worked there, I learned a lot about the capitalism. The question that I had at the company was why the other people do not work like me or do not work like our team. Why don't they work hard? And I just figured out, okay, I didn't know that, but actually there was an incentive problem. Usually when we make a startup, how many percent of the shares do you expect as a CEO or a president or as a founder of the company? We have kind of a formula for the venture games. So maybe I guess you may expect like about 50%, right? And then how many shares you can give you to the 10th your teammate? Maybe it'll be like 0.5%, right? The incentive is kind of 100 times. Here, what I want to talk is about capitalism is not good. It's not the thing that I want to say. Here, founder is not a greedy one because the founder is taking all the responsibility to run the company, all the debt and all the responsibility. So sometimes it works very well for, especially for venture startups, which needs a rocket speed, right? But honestly, I burned out there a lot. So what I started at the time was the open source. Can you imagine what is the difference between my venture game experience and the open source here? Let's think about, source code is one of the most productive means of production, right? Recently, ChatGPT is writing source code and get very productive, right? And it was very interesting to me that, oh, in the open source community, people are giving up their right to commercialize their source code, which is a powerful means of production. And actually that culture was absolutely different with the venture company's culture, because we need to own, and we need to own the kind of 50% of the shares, and we need to run the shareholder economy, right? We need to focus on the shareholders' incentive. But in the open source community, it was like, oh, it just looks like communism, right? Why people are giving up their right and ownership of the source code? What I figured out there was the difference between the communism that we know about, like other countries, and the open source community was the freedom. There was a big difference between those kind of a communism culture and the open source community. Was the big difference was the freedom. So this is the free software movement. We run the software, study the software, modify the software, and share the software by our own freedom. So it's a open source community is a community for the people who takes the freedom as their core value. And then it was kind of a 2017, and I just started to explore those kind of vague communities who are taking care of the freedom. And what I found at the time, the most value-driven community for freedom was, maybe guess, which community? Yes, actually, it is not Ethereum Foundation, but the Ethereum community. But Ethereum was the word of freedom for the old Ethereans. I learned a lot. Like, I visited the DAFCON Prague in 2018, where all the developers around the world getting together and share the ideas. And I was very happy there because in Korea, actually for me, Ethereum was kind of for the community, for the freedom. But when I meet people, we only talk about the ICO and something else, token, investment, etc. And if you want to try to build some project, then actually at the time, people recommended me to make a startup. Oh, by the way, just a moment, please. Decentralization is what? Is a giving up your ownership for the protocol. Actually, decentralized means like there's no owner for the protocol. It runs by a code, it runs by a trustless technology. But people recommended me to make a startup. And actually, so it was very difficult for me to meet those kind of people who takes the freedom as core value in Korea. And when I visited DAFCON, and I finally met people who are really sharing the same core value. Yeah, so that was my journey. And there is a reason why I came into this Ethereum community. And finally, when I just after I just got into the Ethereum community, what I focused on was about mostly the public goods and experiments for the freedom. Let's think about what kind of a public goods and experiments for the freedom. It's just like the privacy at first. It was 2000. I don't remember correctly. It was maybe at the end of the 2018 or the beginning of the 2019. I traveled with my friends and we just split the bill using MakerDAO style. I mean, ERC20 tokens. And a few months later, actually my position in the MakerDAO was liquidated. Do you know what does that mean? It means I lost a huge money at the time. And actually, and my friends were just keeping tracking my Ethereum address that I use for the splitting the bill. And then when my position was liquidated, my friends just texted me, "Hey, I just saw that your position was liquidated." Like, so what's it? Where's my privacy? I was very shocked. And because of that, I started to write and develop a privacy protocol as an open source. So what I did at the time was just implementing the privacy protocol like Zcash on Ethereum was my protocol, was my experiment at the time. So there was a reason, actually, so because of the project, Ethereum Foundation reached out to me and I started to work from the 2019. So it was my journey from like 10 years ago from now until now. So I guess I can give you more, I can share my experience a lot after class if you are just interested into having chimek together 운동. So maybe if you're interested, let's go there. And before we start the programming, I just wanna make sure that there are something that we have to take care. I know that you guys are interested in DeFi, NFTs, and games, etc., right? But there are many things as a public goods and experiments that we can do for the Ethereum community. If you do those kind of things, then actually you are contributing the whole community a lot. So before we start, I just want to introduce you guys about what kind of things we can do in the Ethereum community. The first one is the privacy. This is a privacy is one of the human rights described in the Universal Declaration of Human Rights by United Nations. So no one shall be subjected to arbitrary interference with his privacy, blah, blah, blah. So there is no doubt that we don't need kind of this privacy for Ethereum, right? But there is a problem that still we have a lot problem. We are still depending on the trustworthy party a lot. For example, where are you just storing your photos? Maybe Google Photos, iCloud, right? We are just trusting that. We are just trusting trustworthy party. But what we really need is building the trustless privacy. Let's see what kind of trustless privacy is, right? What kind of trustless privacy exists. The basic one is the end-to-end encryption. So for example, KakaoTalk is not an end-to-end encrypted message. We are storing all the text inside of the cloud server. So if any kind of the employee just made a decision to see that, maybe I'm pretty sure that they can do it. But we need a solution that trustlessly we can keep the privacy. Is the end-to-end encryption. So me and you exchange a shared key and encrypt a message using the shared key and sending the message between us. If that, the third party cannot decrypt the detail of the message. But actually, that is still not enough. We have a lot of things. For example, think about the Apple Siri. You just send your message, you just send your voice to Apple, right? But if we encrypt the data, then actually Apple cannot provide you a correct service. So in this kind of case, what we can use is the homomorphic encryption and maybe zero knowledge proof here for the privacy, to keep your privacy. Actually, zero knowledge proof needs a lot of some base knowledges. So I'm just gonna explain only a little bit about what it is. It is just proving that you know an argument. Let's see some example for about it. An example is just voting. When we vote for the parties, like here, what is the argument is that I have a vote, right? Which means I am a citizen of Korea, right? But what I want to hide here for my privacy is the connection between my vote and my identity, right? So let's see that. The basic structure of the zero knowledge proof is you have a knowledge of argument and its homomorphically encrypted value. And then the verifier can use this homomorphically encrypted value and also use the knowledge argument. It works like you have a citizenship and then you have a encrypted ID and your vote. Then the verifier can use those encrypted IDs and vote without knowing your exact identity, because we have a proof that you are a citizen. This is what we can use for how to keep your privacy using a trustless technology. And there are a lot of some applications and a lot of areas we can contribute to. And let's go to the next topic, the network level privacy. Just imagine like when you vote, like if you have a anonymity, then network level privacy becomes a lot important, because people can do the DOS attack more easily when they have the anonymity, because we don't know where this message is coming from, right? To protect the network, anonymous network, from those kind of DOS attack, we can also have a spam protection layer. Maybe it's kind of a introduction for about the left curve cryptography, which is a basic cryptography of the whole blockchain. So it's pretty simple. Like let's think about, you have a polynomial of degree 2. This is a polynomial of degree 3. This is polynomial of degree 3, right? Then how many points you need to figure out the polynomial's coefficients? Yes, we need 4 points, right? If then, let's assume that you have your private key and you can just pick a random polynomial with degree 3, right? Then we can have an infinite number of polynomials and we can commit that polynomial, but we send a point when you send some message to other, which means if you send more than 4 points, then your private key is just getting revealed. We can use this kind of electrical cryptography and some economical setup using proof of stake. We can build a spam protection layer using this kind of a trustless privacy technology. This is called Shamir secret sharing, and which is pretty simple, right? And very easy to understand and very fun to try some experiments. So maybe in May, we're gonna do some more hands-on session using this Shamir secret sharing, just to get into the elliptic curve cryptography world. And the technology can also be used for scaling. Maybe is there anyone who already has an experience of building something on Ethereum for now? Yeah, maybe we have, and maybe we might have some people also in Zoom. And I'm pretty sure that many people are just awkward, like the developer experience when you build something on Ethereum. That is because Ethereum is not your computer. That is our computer. Ethereum is a world's singleton computer. So it should be very expensive, but we can find some better approaches to how to not to abuse our single world computer. That is the scaling solutions. And for the scaling solutions, we can have two kind of approaches. First one is the computational scaling, and the second is the data side scaling. So first, the scaling for the computation is, just imagine like we have a Ethereum as a work computer, and people request a lot of computations to the work computer. It's not good for all the people, right? Because some people can just take all the bandwidth of the computational resources. So what we can do is, okay, I'm gonna compute them in my end client. And I'm gonna just give you a proof that this computation is correct by cryptographically. If then we can achieve a huge scaling for the computations, because we don't need to verify all the computationals on the work computer. And also, scaling is also same. So, for example, if you wanna store some data on Ethereum, it'll be massively expensive to store some data on Ethereum. So what we can do here is, okay, I don't give you all the data, but these data is including the information that you need to verify some fact. So we can just compress the data into this one small proof. For example, let's think about you. Actually, our hands-on tutorial of today is implementing Bitcoin on Ethereum. So when you implement Bitcoin on Ethereum, you need to verify the ECDSA signatures, right? Then, for example, imagine we need to verify thousands of ECDSA signatures on Ethereum smart contract. It is huge, right? And the data size of the total ECDSA is also pretty huge. It's like 65 bytes per one signature. So we can compress all the signatures. Like, for example, if you have thousands of transactions, the data size for the signature will be like 65 kilobytes. But we can compress all the signatures into one proof that all the signatures are correct. But here's a proof that these signatures are correct cryptographically, and the data size is 256 bytes. It's a huge improvement, right? Okay, so this is what we can do for Ethereum. So there are many these kind of very fun and interesting topics you can contribute to as a public goods, and also you can do some experiments for those kind of topics. So I hope that you are interested in this kind of topics, and if you're interested in, you can just ping me. Maybe I'm gonna share my email or contact through the 조교님 통해서 maybe. Okay. Yeah, I spent about 30 minutes for kind of some stories. From now on, gonna talk about the technical details of the Ethereum. Is there anyone who has heard of Ethereum 2.0? Yeah. So can you explain what is the Ethereum 2.0? Yeah. So today I'm gonna talk about only for some execution layer, but Ethereum has evolved a lot from after its launching. And around 2018, we had a roadmap which is called Ethereum 2.0. At the time, the roadmap was like, okay, we should scale, and maybe sharding the blockchains are kind of a possible way that we can scale Ethereum. But maybe around 2019, at the end of 2018, we figured out that the roll-up approach is much better than plasma approach, which means, okay, now we can think about what's the data layer. We can, at that time, we started to think about, okay, data availability is something different. Then how should we deal with this? The answer was, okay, let's use sharding for the data layer. And simultaneously, we started to think like, okay, maybe sharding the execution does not make sense, because anyway, what we want to do is making only one singleton state for the world. But if we have some shardings, then maybe we need to communicate with the different states for the different sharding chains, and it makes a lot messy. So we abandoned the name Ethereum 2.0. And the proof of stake client that we were developing as Ethereum 2.0 client became a consensus layer. So consensus layer just take care of the proof of stake, the only about the consensus. For example, this block is right. This block is correct with this amount of security, which means the proof of stake. And we just kept the Ethereum 1.x, the previous client, as an execution layer. So there's nothing changed for the execution layer from the previous roadmap and the new roadmap. And then for the data layer, okay, maybe we can use sharding inside of the consensus layer to guarantee that this data will be available by the probabilistically using the polynomial commitment. That is the changed roadmap of the Ethereum from like 2 and 3 years ago. And now we're gonna talk only for about the execution layer of Ethereum. I guess maybe 강민석 교수님 already took this topic, the difference between Bitcoin versus Ethereum, but actually it is crucial to take a look to understand the deeply how it works. So the key difference of Bitcoin, Ethereum in the technical point of view is Bitcoin is array and Ethereum is a key value dictionary. It's simple, right? So we can take a look about how to compute balance in Bitcoin. Maybe the font size is too small, right? Yep. By the way, in Bitcoin, we have a list of coins. So, and also for each coin, we just write down your name. Oh, this coin is mine and this coin is mine. And then we compute the balance like just using the MapReduce algorithm. Okay, just filtering my coins and just sum up that. Actually, that is my balance. And to send my Bitcoin to you, I just collect my coins and create a new coin, spending my previous coins and just giving that to you. That is how Bitcoin works. Then let's see how to compute the balance in Ethereum. In Ethereum, you just write down your balance in the key dictionary map using your account address. So at first, it might be like your account address will have a 0 for your balance. But if someone wants to send some Ether inside of the Ethereum, then we need to execute a function to change the key value dictionary state. So maybe if you have dealt with the store management in React front-end programming, maybe for example, Mobex or Redux, then we have action in Redux and we have state in Redux, right? State store. State store is just the same with the storage inside of the Ethereum. Singleton store, singleton state. We just update that by just dispatch some action, just like in Redux. The action name is the function name, or maybe contract address. And action has a description and definition of how to update the store, singleton store inside of that function. That is how Ethereum works. So if you also have used Redux, how Ethereum works is exactly same with how Redux works. So maybe you can just read this code and you can find this code is pretty similar to the Redux code. And to add some cryptographical components into this setup, what we use is the Merkle tree. So I think you might heard of Merkle Patricia tree, and maybe some of you are familiar with the difference between Merkle tree and Merkle Patricia tree, but some of you might not be. So the difference is Merkle tree is just a list. So you can think, okay, Bitcoin is using Merkle tree. And Merkle Patricia tree is a key value dictionary. Let's see how it looks like. So the left side is Merkle tree. So you are just listing up all the items here, A, B, C, D, E, F, G, H. And we are just folding up these leaves when it becomes one. Then we have a root of this data. The reason why we make this kind of structure is to prove that there is something inside of your root hash. So because is there anyone who is familiar with how Git deal with the file system? It just hashes everything. It hashes the list of the file. So file will have their own hashed object hash, and it's a directory just hashes everything, and its parent directory hashes everything. So if you have thousands of items in a directory, to prove that an object exists inside of Git, you need 999 other objects hash. But in this approach, we have 8 items. But to prove that something exists here, then what you need here is sibling data for the path. So this one item and sibling, and root. You don't need kind of 6 other hashes. That is the reason why we are using Merkle tree for Bitcoin, to prove that you have a leaf inside of Bitcoin. Then how about Ethereum? How about the key value dictionary? So we developed the Merkle Patricia tree approach, which is assigning value inside of Merkle tree, and all the leaf here will have their own index. So this is index 0, 1, 2, 3, 4, 5, 6, 7, for example. Then if you want to store some value at the index number 5, then you're just putting some value here. But in this example, I just used foo bar bars example, and we can just think like, okay, foo index is here, bar index is here, buzz index is here. So we can store some values inside of this Merkle tree in a verifiable method. So we can verify the value of bar is 2 because the hash of this one, and we can compute the sibling and sibling, then we can just prove that, okay, we have a value inside of the Merkle Patricia tree by the n hashes to prove that. Okay. And this is a more detail of the how exactly a Merkle Patricia tree looks like. So there is a binary version. So you can think, okay, the index here, index for each node is, the root node's index is 1. And this one is 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Not that interesting. So yeah, by the way, we also can have a hexagonal version of Merkle Patricia tree. So what Ethereum is now using is this hexagonal version of Merkle Patricia tree, but we are preparing the upgrade to change this Merkle Patricia tree structure for the state management to the vertical tree, which is using a polynomial commitment to prove a state data. Okay. And then let's take a look about the block structure of Ethereum's execution layer. It is too small, right? Can you read this? Okay. Okay. So let's take a look what exists inside of the header. But you don't need to read this. Just imagine and think about it. What data we should have inside of a block header? What kind of data? What kind of data? Yep. Yep. Definitely parent hash because this is a blockchain. So a block needs its parent block's hash inside of its block header. Then what others? Yeah. So inside of a block, we include transactions to change the state, right? But block header is for the metadata. So if you include all the transactions into a block header, it doesn't make sense. So we construct a Merkle tree using the transaction hashes, and then just put the transaction hashes Merkle root into the Merkle into the block header. And maybe the block miner can write down the gas used. Block miner can write down the timestamp of the block, or block miner will write down the address to get the miner reward. Does it make sense? And those kind of information is inside of the block header. And there's two things we have to look at it here. One thing is we store the root of the Merkle Patricia tree of all the accounts. And the other one is a log bloom filter. I'm gonna, okay, let's take a look at the log bloom filter first. If you execute some transactions, then it will changed the state or failed. So if you change the state, then we can log something. So maybe if you have ever used Etherscan or something, then maybe you saw some event that some ERC20 token sent to a recipient. It is something like logging something, but how to find that? How will you find the log from the blockchain? The data is like more than terabytes, and you need to just scan all the data of all the blocks and just discovering how the state changes happen there, occur there. So to prevent that approach, we just leave some simple Bloom filter to help you find your log. So okay, let's see how Bloom filters looks like. Yeah, you can see it, right? So Bloom filter is basically we can have a 8 bits Bloom filter or 16 bits Bloom filter or 256 bits Bloom filter, but Ethereum is using the 256 bits Bloom filter. But let's assume that we have a 8 bits of Bloom filter. Then we have 8 bits here. The initial filter just looks like this. Every value stored in the Bloom filter is 0. And let's assume that you have a event sent. And let's assume its hash value is like 37. And then we divide this 37 with some numbers. For example, let's divide this number with 5. Then what becomes the remainder? It's 2, right? Then mark this one is mark the index number 2 to 1. And also divide this one using 7. Oh, then not 7, maybe 8. Then the remainder is number 5, right? So then mark index number 5 to 1. So we just record the accumulated result of the remainders into a log Bloom filter. Then if you just take a look and okay, my event is sent and its corresponding log Bloom filters indices are 2 and 5, then we can just take this is marked or not. If there is a Bloom filter, which looks like this, it definitely doesn't include the sent event inside of this block. Using this approach, we can scan much more faster to find a specific event that you want to find from the block. Okay. This is how the Bloom filter works. And then let's see the transactions. Before the transaction, let's see the state tree of Ethereum. Okay. So in the Ethereum block header, I said we store the state tree of the all accounts in the state tree root, because we should be able to verify some data, some value exists in a certain index. But in Ethereum, we have some different storage structure to make a permission control system. For example, let's just imagine like we have our own computer and we are connecting our old computer as one world computer. If then, should I be able to change some data inside of your computer? No, right? We need a permission. We need a permission to change some storage data inside of your computer. So to change some data, you need a permission, and we are controlling the permission using the signature. So if you have an account in Ethereum, and if you can make a signature to send some Ether to another account, then it is allowed to do that, allowed to do the state transition. But if you do not have the correct signature or correct permission, if you do not have, then actually you can change the storage. So to implement that approach, we have a word state tree. And word state tree is a Merkle Patricia tree of all the accounts. So all the accounts index becomes the account's address, and we have the hash value of that account, and we construct a Merkle Patricia tree and call that as a word state tree. And we store the state tree root inside of this block header. Then let's think about, if you have a block header of block number 11,047,000, then can you prove that you have a one Ether in your account using the block header? The answer is yes, because it's based on the Merkle Patricia tree. So we can go to, okay, here's my address, and I can make some Merkle Patricia tree proof that my account is here, and the hash of my account value is something like this. And here, what we are using inside of an account is also, we use Merkle Patricia tree inside of an account too. So you need to understand how an account looks like. So an account has 4 slots to store a value. The first one is nonce. The second one is balance, and the third one is storage root, and the fourth one is code. Let's see about the nonce at first. When you want to send some Ether to other, you create a signature, right? Then, actually, let's imagine I am the recipient of the Ether's transfer. Then, just to get recurring the payment, I can use the signature again, right? Is it possible? Actually, that is not possible, because when you create a signature, you need to include a nonce value to the hash to sign data. So if we once use one signature, then nonce should increase 1. So nonce starts from 0 And if you send a transaction, nonce becomes 1. And if you send a transaction again using the nonce 1, then the nonce becomes 2. So this is the first value inside of the account. And the second value balance is literally the balance of your Ether of the Ethereum account. So the reason why we need balance here is because of the gas. You need to understand what gas is here, because I just said multiple times today that Ethereum is a word computer. So computing something on Ethereum or storing something on Ethereum is expensive. So we labeled each action a price. For example, storing some value inside of an account is kind of a $1. Or only sending some Ether is kind of a, okay, it's 10 cents, like this. And that is called gas. And gas is the gasoline, and Ether is maybe in Korean ethereum, the fuel. So actually it just implies that Ether is just designed to be used as a fuel. So if you want to make some changes inside a blockchain, you need enough fuel to change that. So the balance can be just considered as a how much balance, how much amount of fuel you have. And we just gauge how much fuel we're going to use as a gas price multiple times the gas amount you used. That is how Ethereum is designed. And then we have a storage here. So as I just talked, we can store all the values inside of this small slot. So we only store the Merkle Patricia Tree root inside of here. And then here's something suspicious slot, which is called code. Can you imagine what it is? That is called smart contract code. So we have two types of accounts. Account which has a code, or account which doesn't have a code. So that is called external owned account, which will be used by a user. Or there is an account which has a code, so which can do something, which can make some changes inside a blockchain by themselves. So we have these two kind of accounts. Then let's think about you are creating your own Ethereum account. What happens? What happens is you're just creating an account without code. And it will have a nonce balance, and actually the storage root will not be changed. So, but we create this account in a very lazy way, lazy approach. We do not make all the accounts because it's a 2 to the 20, so it's a huge number. So we do not make account before, and we just create them in a lazy approach. And how will you make a contract? Making a contract is creating an account using this code. So you can send a contract creation transaction to the Ethereum, and using the code to make this account. Okay. Then for the next step, let's think about how we can execute a smart contract transaction. Just one, please. Okay. So to execute a smart contract transaction, we need a function definitions inside of a code, just like Redux. So code is a set of the definitions of what we're gonna do if someone execute this function. So people will execute a transaction against this account with a given function name. And then the execution client matches the given function name in the form of selector, which is 4 bytes, inside of the code, and then bring the execution byte codes and run that. This is how the smart contract works inside of Ethereum. Okay. Do you want to have some rest, or maybe? Okay. Let's take a 10 minutes break.